Let's start with the easiest part of the transport layer, TCP. The goal of the transport layer is to provide an abstraction of the network that is usable by applications. Strictly speaking, the transport layer is really the lowest level of abstraction that we will see in the map. There are many supplementary abstractions that you can add within the application layer. It's very important to understand those two abstractions of the transport layer, which are UDP and TCP, because they affect the way applications are written. There are two transport layers. Every 2 years, somebody tries to sneak in another one, but so far today, it's practically only two. All other high-level abstractions are built on top of UDP or TCP. There is no TCP V6, nor UDP V6, nor UDP V4 or TCP V4. That's the good news. The transport protocol TCP or UDP is the same whether you run on UDP on IPv4 or IPv6. In some sense, it's a success of the layered approach that by changing to IPv6, we don't need to change the switches below, except for the path, and we don't need to change the layers above. There is no TCP V6, but there are IPv6 sockets for TCP. When it comes to programming, you need to have explicit IPv6 support. For example, because if you connect to a web server, you have software that has been written 20 years ago and works only with IPv4. When you do resolution of the IP address, perhaps this server has no IPv4 address, but only an IPv6 address. And the software will be unable to handle an IPv6 address. It's 4 times more big than the IPv4 address, and there will be no space in the data structure to fit this address. So it will not work. You need to write code for IPv6 or IPv4. Sometimes it's misunderstood. There is a TCP V6 or a TCP V4. No, there are TCP V6 sockets and there are TCP V4 sockets. The protocol itself is the same. Now let's talk UDP. We have seen UDP port numbers. We use them in maths, for example. Here is a second password. The port number is a logical number that is an address at some time. Every layer has its addressing scheme. On the IP layer, we use IP addresses. On the UDP layer, we use UDP addresses, which are port numbers. What does an address mean in that case? So the port number means the address of something within the environment where the transport layer is working, namely within a machine. So it typically means within something that I can reach by an IP address, there can be several things that I can talk to. For example, you can think of them as applications or processes. Here I'm showing one process which responds to port number 53. It's called the DNS server. On this machine, you could have a DNS server, but you could have a web server, for example. Most machines, network machines, have web servers that are used for configuring them. So you can also perhaps SSH into it, so you can have several application programs that are running, and you need to, when you talk to one of them, you need to specify which one I'm talking to. That's called an addressing mechanism. But now the addressing is local within a machine. Strictly speaking, local within how you reach this machine from which IP address. Port numbers are typically classified into the ones that are below 10 bits and the one above, so the up to 1000. So 53 is all the lower values are in principle privileged, and when you do the lab for programming, you cannot, in principle, unless you are a super user and you do something will not be able to use this port number. They are meant to be used by standard services. Many of them are even standardized. For example, 53 is reserved for DNS. I'm showing here also a DNS client, which uses a different port number from this machine. I'm using UDP to send a query to the DNS server. What is the IP address of that machine, that name? And this one is not using the DNS port number, it is using local port, which has no meaning. This port number is still necessary because you can have many programs running in the machine, receive this port number when the program starts or whenever there is a need to do something. We'll see that when we talk about sockets a bit later. This is called ephemeral port. Also this one, which is permanent port. This is also often equivalent to the server port of the client. The server, remember, however, a server is the role of a transport layer entity that is listening. When a machine A wants to talk to machine B, you need that they are both active at the same time. If I have a DNS server program somewhere, I need that this DNS server program is working before I contact it. In contrast, my client program needs to run only when I need it. It doesn't need to be, my machine is down or is not doing anything. My client program doesn't need to do anything. So by definition, a server is the role of a program that is working in the background, listening for some message to be sent to it. It corresponds to, very often in practice, to a process or a task that is forked, that is launched in the background and is running in the background. Very often we call that the daemon. So a server corresponds to a daemon, and very often, but not always, the server port is the well-defined port. So when this guy sends a query to DNS, it uses UDP, which means that there is of course an IP header. Inside the IP header, there is a next protocol in IPv6 or a protocol in IPv4 that says it's UDP, and then UDP itself has its own header that contains essentially the addressing information, like any header, source and destination, UDP source port, UDP destination port. In this direction, it will be 53 for the destination. A length indication that will say how many bytes there is here, and a checksum that is used, that is a primitive form of error detection code that verifies, in principle, UDP data, also the IP destination address, and the data. How does a DNS client know which port number I should use? In principle, we could use DNS for that. I could put in the DNS, my web server is on this port, but this is very, very seldom used. In practice, we use some other mechanism, which for DNS is to use a well-defined port. So if you go to the DNS server, you go to port 53, all DNS clients for that. If you go to an HTTP server, to a web server, what do? How do you know which port number the server now are anticipating a bit? It's TCP rather than UDP. Well, similarly, normally you send to port 80, which is reserved for the web. Or you have an out-of-band mechanism in the name of the server. You can put the port somewhere. Sometimes you see a column with another port number. It means use this port number. In other words, we don't go to DNS or something like this. We go to either well-defined port numbers, or we know it from the application, from the text that has caused this interaction. How does the DNS server know to which port number it should send the information back? As usual, by looking at the UDP source port. So the UDP source port is used to send the information. UDP is connectionless. That's its main advantage, that's why it is used. Connectionless means, what is a connection? A connection is equivalent to state information or synchronization. Those are synonyms. State information means when A talks to B, B needs to have somewhere a table or some data structure of some kind in order for the communication to be able to occur. And this table is specific to whom I'm talking to. Connectionless means, no, there is nothing specific. When a web client, when a DNS resolver talks to a DNS server, there is no state information in this server about this client. Of course, there is state information, which is the DNS database, but this DNS database is not specific to the fact that one machine or another one is asking the question. guy receives the UDP packet, it can do everything it has to do just by looking at the packet. It doesn't need to remember things of the past that could be stored somewhere in local state information. That is a main feature, and that's why it is used when it is used. Servers, for example, that are submitted to a large number of potential interactions find it good to be connectionless. It's much easier for a server to be connectionless because you don't need to bother the state information of many clients. Second, in addition to be connectionless, UDP has a special property. It is message-oriented, which has nothing to do with being connectionless or not. Message-oriented means that the UDP service interface, remember the service interface is the interface between something that uses UDP. So you as a programmer in Lab 3, when you use UDP, you use the UDP service interface, which is called the UDP socket. So through the service interface, we have the concept of a message. I send or I receive a message. This seems obvious. What else could I send? Well, what else is what TCP does? TCP, in contrast, doesn't, of course, you give to TCP a message, but TCP will send a stream of bytes. It might break the message into several pieces. You have no clue with TCP when the message, the original message, started and where it ended. In UDP you do, which means when you are writing a receiver in UDP, you read from the service interface, you ask UDP, give me something, UDP will give you one message. One message means it will give you exactly the number of bytes that were sent by the receiver. Not half of it, it will not put two messages into one, it will, for every call, give you exactly one message, which is an essential property if you want to do simple applications, because if you send a query to a web server, to a DNS server, if you send two queries, you will need to call UDP twice, and the DNS server will need to call also receive from UDP twice, and we'll know exactly each of them is an entire message. So you don't need to have a MIME header or things like this that we need when we use TCP, for example, to declare how many bytes there are in my question and things like that. So it makes the job of the programmer simple. Of course, there is a maximum message size. The maximum message size by default in UDP is that number here, 64K. Very often, this is larger than the maximum packet size of IP. If this is larger, then there will be what is called fragmentation. We will discuss a bit later when we talk about the last bits and pieces of the IP layer. If the message is too large to fit in one IP packet, it will be broken into several IP packets, and at the IP layer, and the IP layer will reassemble all these elements and deliver it to the transport layer. Which means that if you write a very long message, for example 2,000 bytes, it will need two IP packets. When you do a receive call at the other end, if only one of the IP packets has arrived, UDP will say, sorry, there is nothing. So it will be as if nothing has arrived, because fragmentation occurs at the IP layer, not the UDP. The UDP sees atomic units, which are messaged, 0 or 1 message is sent, and 0 or 1 message is delivered to the application. Questions?
So when it says not visible to the application program, it's also not visible to the application.
Yes, it's when I say invisible to the application program. Is it visible to the transport layer? In principle, it is not visible to the transport layer. Here is a very simple UDP client and server. So I'm writing a UDP client that sends one message, and the UDP server that receives one message, perhaps displays it. Not a very useful program, but that's the simplest of all programs that we'll need to do. What do we need to do if we use UDP to do that? Well, we need to, this is in Python or C, we need to create a socket. A socket is an interface in which you can write. In Unix and Windows and Macintosh, therefore, it is equivalent to a file descriptor. So writing into a socket or reading from a socket is the same as from a file. In fact, I use the word writing and reading, which are words we use for a file. When you have a socket, you think of them as sending or receiving. But from the syntax, even from the way the operating system handles them, it's similar to a file descriptor. Now, you've done that many times, probably. When you write into a file, first you need to create an interface in which you can write, which is done by the socket call. Then you need to do things like bind. Bind typically means giving a port number to this socket. Normally, if you're on the client side, you give bind with no arguments. That means the operating system will give you a port number, and as a result of the bind, you will know which port number this socket corresponds to. On the server side, you typically, the server, classically, you can imagine different ways of organizing your code, but typically the server uses a well-known port. So you define which port this application will respond to, and then when you do the bind, you ask the operating system the permission to use this port for you. If it fails, well, you need to handle the exception. If it doesn't fail, then it means this socket is associated with this port. When you have done that, you can send one message, and I said you write into a socket. It's not exactly true for this example here, because UDP is connectionless. You need to send and send to whom you are sending. You need to give the destination port and the destination IP address. So this is done by something called send to. And then if that works, this will be sent over the network. And on the receiving side, you need to do receive. And since you don't know with UDP who is sending to you, your server can receive from many, many different machines. You will know who is sending to you by looking at the source IP address and source number, which you will get by doing a receive from. So receive from will tell you whom it comes from, plus it will give you one message. When you issue a receive from, typically, if you don't manipulate the socket option, it will block until one message arrives. Like all system calls block until they work. When you send, it blocks, but in principle, it's a very short time to send, so you don't see that it blocks. When you say receive from, and nothing has arrived because nobody has sent to you, or the packet that has been sent has been lost, for example, then your receive from will block. That means your program is stopped. You want to catch the thing, you can give maximum time to the blocking, which is something we'll learn to do in the app. And then when this arrives, it unblocks the dots here, and then you can receive it and display it. In principle, that's all you need to do. If you're well educated, when you close your program, you also close the socket. Because the socket is a data structure inside the operating system that uses resource. If you don't close it, you're not 100% sure the resource will be released. And that's one of the sources of what is called software aging. Programs that crash, for example, or that close without closing, may leave some operating system resources that the operating system still believes somebody's using it. And if you do that, if you're a server, if you're a laptop, it doesn't matter because you reboot once in a while. If you're a server that's running for years, then you might softly start losing some of your resources. You might need to be rebooted once in a while. Avoid it, it's better. Questions? There is, as I said, no UDP-V6, but there are UDP-V6 sockets, so you need to specify whether you use UDP-V6 or UDP-V4, and this is done by, when you do the socket call, for the zillion possible arguments, one of them says whether it's an IPv6 or an IPv4 socket. Here is a mental view, which I believe is the most useful view of what sockets mean in the operating system. Application programs write or read to and from sockets. There are IPv6 sockets and IPv4 sockets. There are different things. When you open a socket, when you create one, you have to say Each socket has probably some form of buffer, which is used for storing things when they arrive, and also when they are sent. When you send data, you need to store them because the speed human beings perhaps sending is instantaneous, but the speed of the instructions of the program, it is not. You need to pass things to the IP layer, to pass it to the Ethernet header. The Ethernet layer, is probably in another piece of hardware, so you need to communicate via the bus with the Ethernet header, with the Ethernet adapter. Maybe busy doing something else, or the bus might be busy, so it might take some time until your sending completes. So you need to buffer things. But certainly you need to buffer even more on the receiving side. If somebody sends data to you, then if nobody is listening on this port, that means if no program has done the socket call with this port number, the operating system will discard the packet. Nobody is listening to that. And will send an error message in many cases back to the source saying there is nobody listening. It's impossible to deliver that data. If an application program has issued a socket call to that port number, when data arrives, it's put in a buffer. Now, hopefully, the application program will read it, but the speed at which the application program reads is not correlated strictly to the speed at which data is arriving. In fact, with UDP, it's not correlated at all. You could have a DNS server that receives data from 1 million DNS clients, and the DNS server is unable to handle that. It's slow compared to the load it has to support, and then the buffer will overflow at some point, which means there will be a problem with the server performance problem. The TCP will manage this performance problem by what is called flow control. With UDP, we don't. The idea of UDP is we send one short message. There is no management capability because my DNS client sends one message and that's all. I cannot slow it down. IPv4 packets are treated differently than IPv6 packets, so for all practical purposes, there is an IPv6 stack and an IPv4 stack. IPv4 packets that come to this address are demultiplexed by looking at their port numbers and go to different socket buffers. So the same socket buffer can be used to communicate with different sources, different remote systems, if we use UDP, as in the case of a DNS client server. Well, now, that's all, at least at the theory level for UDP, which is very simple. A quick question here. This name resolver uses UDP. What happens if either the packet or the answer to that packet, the query, is lost? Tricky question because of the number of the above. But perhaps not so tricky after all. I close in a few seconds. And this is the correct answer. Majority seems to be always right in this part. The message can be lost with UDP, as we have seen several times. That's the main feature of UDP, which means that message losses have to be handled by the application. Now, for the DNS resolver, there is the semantic of the application that makes it very natural to ask a question. You wait for an answer. If the answer doesn't come, or if it comes, then you can use it as an acknowledgement. So you can use the presence or absence of answer as a detection of loss. If no answer comes, probably you need to wait for a timeout, then you send again. This is exactly what the DNS protocol says we should do. Of course, you need to be careful when you send again. You should, if it is lost because there is congestion, for example, on the server side, by sending it again, you will continue or even make congestion worse on the server. So what should you do to avoid this? Well, in DNS you typically have several DNS server addresses. So you can try another server. But typically before doing that, you will try several times with the same. But when you repeat the request, you will increase also your timeout. So I send a request, I wait 1 second, nothing comes. I try again, and then I wait 2 seconds. Nothing comes, I wait 4 seconds. And then I give up and try a different server. By doing that, I will make sure I'm not doing closed loop feedback into the server. I'm not doing avalanche storm on the server. If there is a loss, I reduce the rate at which I'm trying. In principle, if you do have a Unity application, you should think of those things. Question?
For the name of resolving, the IP address of the DNS server is given by the TCP protocol.
Yeah.
And does it give us all other backup DNS server address in case we cannot contact that one?
Yeah, you should. I mean, if you look at your configuration as you've done in the lab or in your machine here, not on your iPad, if you have a PC or a Mac, you will see that typically DHCP gives you several DNS servers. In fact, you always need 2. That's a good practice. And if you provide one DNS service, you should at least give 2. Now, companies like Google, they give you several addresses, 888 and others. Even behind those addresses, they have several machines. So they have tricks to make it possible to have multiple machines corresponding to the same address. We'll talk about that trick again a bit later. Called any cancel. Alright, that's for UDP. UDP is very simple and beautiful. Now, of course, having to manage and handle the losses is not very nice. Building a web application, like you will be also doing in the lab. You will want to have to put counters and timers for every packet you send. You would like this to be done once for all. This is done by TCP. Now TCP does this, but also it does it in its own way, which is a bit special. How does TCP work? Or what does it do exactly? Well, it guarantees that all data is delivered, but it adds one thing, it guarantees that it's delivered in sequence. If you send 5 blocks of data, you could imagine doing a protocol that guarantees that the 5 blocks, you will do everything that's possible to repair the losses and deliver you the 5 blocks. But if there is a loss in only the second block, for example, probably that would mean that you receive block 3 before block 2, because repairing the losses probably means retransmitting packets that will take some time. So a simple protocol that would do error correction, repairing of losses, would probably not respect the order in which the messages are sent. Which for many applications doesn't matter. For example, you're downloading data from a web server. You have a web page that has zillions of animations and things and all corners. Each of them is identified with a MIME header. So this is an image, it should be there on the page, etc. So whether you receive them in exactly one order or the other, they will all display nicely in the page. So that doesn't really matter for many cases. TCP believes it matters and forces things to be delivered in exactly the order that they were sent. If you download a non-TCP connection from the web server, if one of the objects has a problem, then this will delay all the others. You will until the losses are repaired. That was important at some point in the past. It's important for some applications, for others it is not. But this is what TCP offers. It doesn't offer anything worse than that. Let's see. Let's talk about that. TCP is both very complicated to use and simple, and it's also complicated to understand. The basic principles are simple. I'll try to explain the basic principles, but it's not too simple. So it will be a bit complex. So the basic operation of TCP is explained here. When there's no magic, how can you use the? Here I'm using the differential encoding method. I imagine how I would do it. Imagine how you can read there, losses. If you do it at the application layer, you send chunks of data. You want to be sure they've all arrived correctly. And a very simple way is to put numbers in each of the chunks. Remember the numbers one by one. And you expect that the destination sends you acknowledgements for the chunks. And this is the basic mechanism that's used practically everywhere. Now TCP does not do it exactly this way. There's a delta to remember. TCP does not number the TCP segments. So when you send a file, a video file over TCP, TCP will break it into TCP PDUs, TCP packets, that are called segments. You will send, for example, 1,000 packets. You will not number the packets from 1 to 1,000. It will number the bytes in the packet. So TCP uses sequence numbers that are bytes, as if every byte was an individual packet. Of course, TCP doesn't put 1 byte packets, with as large packets as possible, but it will number things by byte. That's what makes TCP a bit awkward or efficient, as you want, which is illustrated here. So, for example, on the top, we see A is sending 500 bytes of data. They are numbered. So there is a sequence number, which is in the TCP header, which is 800 to 800, 500. Now, the TCP folklore always adds 1. So the first byte is 8001. The last byte is 8500. But in TCP, we always put the next expected number. So that we take the difference and we have the length. This is because we wanted to simplify how to compute the length of a packet. Largest sequence number minus smallest sequence. B receives this, and we ACK will send an acknowledgement saying I've received everything up to and including 8,500. The ACK will say I'm expecting, therefore, the next thing to be 8,500 over. Now, the source continues, sends 3 packets, 2 of them get lost. This packet is received, then assume this guy sends an ACK. If it uses the basic ACK, we'll see that there are a few variants. It will ACK what it can, which has been delivered in sequence. So first thing to remember, the ACK field in TCP is how much you have received in sequence. If you want to signal that you have received things out of sequence, we'll use another field that we'll discuss in a minute. So this guy has received up to this number in sequence, so it sends it out. Now the ACK can be lost as well. So assume this one is lost. Sooner or later, the source will realize that the ACK has not arrived. So TCP uses time. As soon as the segment is sent, TCP starts a timer. And when this timer expires, TCP retransmits. Other things occur, so we'll discuss later when the timer expires. But the very basic thing is to retransmit. So we will retransmit this packet here. And when this packet is received, now it can be delivered. So delivered means what? It means what? It means it is available in the socket buffer. And if the application does a read, the application can also read that data, see what has arrived. If the application does not do a read, then it will stay in the buffer waiting for the application to read. And here we will ACK everything that has been received, 901. When this is arrived here, perhaps using this or another heuristic. So this was a repetition of packet at time 3. This is a repetition of the packet at time 4. And now this is because this packet has been possible to be consumed by the application is the data in this, the data in that. So the data in this packet that has been received is available in the transport layer. The transport layer knows that this data has arrived, but it hides it from the application. If you use TCP sockets, it's impossible to know that this application, data has arrived. Because the TCP job rule says you should deliver things in sequence. So this is the very first operation. As I mentioned, this ACK number is not sufficient. You would like to be able to signal to the source. For example, here, not only I have received everything up to this number, but also I have received that other one, so that the source doesn't retransmit this one. We will do that by, to do that, we need to describe something that's more complicated to describe. We need to describe not just the balance thing. I received everything up to 8,500, but we need to describe intervals that we have received. In TCP, we do that by using a SACK option that is in the TCP header. We can have, I believe, up to 3 SACK options that allow us to describe this. We have this payment path like cheese with all single values. So with this, now the source knows that if it has something to retransmit, it's only the blocks 3 and 4. Which it might do here. If you look at the thing carefully, you will also notice that at line 8, the source transmitted 1,000 bytes, whereas before it was transmitting 500 bytes. This is very typical of TCP. TCP does not respect messages. TCP offers a stream-oriented service, which means TCP believes its job is to deliver all the bytes that have been given by the source to the destination in the order in which they were sent, in which they were issued, but not necessarily with the same boundaries. Perhaps the source is an application program that does video streaming and has video packets of 500 bytes. So whenever the codec is ready with one packet, it sends it. Therefore, TCP also sends it. Now, if a packet is declared lost, 2 packets are declared lost, now this TCP has to resend the data. Now, TCP can create packets up to 1,500 bytes, perhaps, in this case, which is a very common case. Then, there is no reason to resend 2 packets if you can put the 1,000 bytes in a single packet, so TCP will, in that case, always try to optimize. We'll try to optimize 2 conflicting things, send the data as soon as possible, which might involve sending short packets, but also try to avoid sending many short packets one after the other. If TCP feels that there is no need to send 2 packets that could be sent together, then here this is an obvious case where TCP knows I have to retransmit those 2, I will retransmit as well. Which means on the receiving side, you have no clue. When you read data from TCP, you cannot make the assumption that when I have all of a sudden 1,000 new bytes that are arriving, you cannot make the assumption that the source has sent exactly 1,000 bytes. Perhaps the source has sent 2 times 500 bytes, 2 messages, or 1,000 messages of 1 byte, or 500 messages of 2 bytes, or whatever other combination. TCP will not tell you that's the way it will. Of course, when this is received here, it will ACK everything that has been received, and there's no need to put the SACK, because the ACK tells everything. I mentioned before that TCP will hide things. TCP has a buffer in the socket buffer that's called the resequencing buffer, and this is exactly what has happened in this case here. This packet, which is out of sequence, of course is kept in the, you don't drop it, you keep it, but you don't show it. Now if you do a read from the application here, you can read at most 500 bytes. You can read this, but you cannot read. It's visible to the application. Et voilà, we will